Hello everyone. So I realized what I didn't do previously was show a little bit about how to kind of do that transition between a two-dimensional and a axisymmetric model. So they're very, very, very similar in setup. Almost, but not quite identical. They both use a two-dimensional simulation plane. However, the thing that they're simulating can be very different. So what I have pulled up here. Let's see here. Where's my mesh scene? There we go. Is my double wedge problem from previously. So I believe this has a solution in it. Yeah, we can see the shockwaves and whatnot. Shockwave, shockwave, shock interaction, expansion fan, etc. Uh, However, if we want to make this axisymmetric, we need to make a couple of changes here. So I'm going to save this as a double cone instead of a double wedge. Because right now this is a two-dimensional wedge. It's assumed to be symmetric about this lower axis, because this lower boundary is a symmetry plane, which means that this boundary acts as if the flow on the opposite side of the boundary is exactly the same as the flow on this side. Now, so this is effectively emulating the leading edge of a double wedge, which would extend directly into and out of the string. The double cone would be something that acts like it's revolved around this axis. So let's just make sure that this axis is actually at 0, 0. Yeah, so the leading edge of this cone does indeed appear to be 0, 0. Let's just confirm this by checking. Yep, the leading cone has a start coordinate of 0, 0, 0, so this is the origin. Right here. That is the origin right there. So if we want to make this axisymmetric instead of two-dimensional, first things, we need to modify our physics. Right now, these are two-dimensional physics. That is not what we want. We want axisymmetric physics. And you know it's complaining about 0 or negative radial coordinates on a non-axis boundary. However, the boundary it's complaining about is actually this lower boundary, the bottom surface. So we need to change this to say this is the axis of symmetry. Go ahead and change that right there. And then we also have an axis here. We want to say it is symmetric about the x-axis. So let's look real close at this. As a matter of fact, let me go ahead and take a screen capture of what this looks like really fast. We'll just put that off to the side for the moment. And what I'm going to do here is run this some more, and we'll see what happens to the shock angles. Bring back my scalar scene. This is probably going to take some time to figure out what's going on here. But we'll let it do its thing for a little while. And we should probably keep an eye on these residuals. Honestly, this wasn't anywhere near converged before either. But you can kind of see what looks like it figuring out a new shock angle that's lower than the existing one. The existing one was up here, and the lower one appears to be figuring it out somewhere right about here-ish. Again, this is not converged, don't get me wrong, but we can kind of spot check this. Let me actually if we turn, because we know that these shocks actually lined up pretty darn well with where our mesh was refined before. So if we turn on the visibility of our mesh, one second, let me stop this from running. We turn on the visibility of our mesh, we can see that these shock waves are nowhere near where they were before. It's actually a little bit hard to see, but this shock wave, instead of being almost straight up here, is at like half the angle, and this shock wave is also at a much lower angle. So let's say that those angles are approximately half-ish. So I'm going to call this 20.5 degrees. And we're going to call this so if that was 40, that's definitely more than 30 degrees. So we're going to call this 35 degrees. And remesh. And theoretically, I think these refinements should land closer to where we're kind of really interested in them being. And notice that the simulation looks just in general a lot less stable because it's got all kinds of weird stuff going on up here because there's shockwaves interacting and doing things where actually this is the shock interaction because we have a shockwave that leads up here, we have a shockwave that comes here, so this is the shock interaction here. But it's doing weird stuff because those cells are very coarse right here because our shock angle went down. This is now a dual angle cone instead of a dual angle wedge, and the shock angle changed as a result quite dramatically. So we're going to let this finish up its 2D mesh. We should see these cone angles adjust dramatically. We might need to mesh it again. And we'll run it out a little bit more. But what we've seen so far is, for starters, the basics, and it's really only a couple of steps, in how to go from a already working two-dimensional model to a axisymmetric model. There are some things you might need to change, as we can very clearly see here, but the change itself was very simple. I overcooked that a little bit. We need to back off those angles. So we'll call this 25 degrees. And we're going to call this like 50 degrees. No, actually, I'm going to abort this really fast. So what I'm going to do, because we could sit here for a while just doing guess and check, I could actually do some measurements here and figure out a little bit more precisely. But what I'm going to do is back off this value to like 40% and mesh it again, which should let this run a lot faster because it'll have a lot fewer cells. We'll see where these regions land, and then if they land in approximately the right spot, then we will go back to the 10%. So that's pretty close. I'd like to back off this initial shock angle a little bit more. We'll go 28 degrees. Let's try that. I think this shock angle is pretty good. Yeah, that's probably fine. So we're going to back this back off to 10 degrees. We're going to remesh. Let's take a look at this. And yeah, you can see this used to be one cell right here. This entire thing used to be one cell. You can kind of see by the patchwork nature of it. And the semi-hexagonal nature. So once we run this, it'll figure out what the flow is actually doing in these areas. So we'll let this run out some more here. We should see some pretty large changes in this area pretty quickly. Yeah, you can kind of see how it's winding up softening the boundaries between those and figuring out what's going on here. So I'm gonna see here. I'm gonna make this mesh scene somewhat transparent so it's less obvious that it's there. We can kind of see where the cells are denser and where they're not as dense still. We look real close. But more importantly, we can see very clearly where the shock angles are, and they do fall within those refinement regions, albeit barely in a couple of cases. At least I think. Let's turn this up a little bit. So again, the primary takeaway is this is now an axisymmetric case. This is a cone, not a what I'm looking for. This is a cone, no longer a wedge, and the shock angles change pretty dramatically. As a matter of fact, we probably still want to adjust this one right here. Let's see here. Start radius, end radius. I want to up the shock spread angle. Something like 3.5 degrees, I think. But anyways, I'll mess around with this more later. This wouldn't just apply to something like this. This would also apply to anything else you care to simulate. So I'm going to save this and switch over to the fin simulation here. So I'm going to save this as a slightly different name. This is going to be a concentric fin simulation. These are the only change we're going to make. We're not going to redo any geometry or anything else like that. What we are going to do, pull up the mesh scene so we can see this, is we're going to make this axisymmetric. At least, well, actually, two things. I'm going to remove the advanced part, which we really don't need. I'm going to remove the advanced part, which we really don't need. we have a whole bunch of boundaries. So these boundaries are going to be still walls, but we're going to make them just a fixed temperature, and we're going to do a brief simulation to see, okay, great, what does the flow kind of look like? Um, what does the flow kind of look like once, we let it converge a little bit? So 300 is 23. If we want this to be up at 90, we need to add about 70. So we're going to do 370 Kelvin. So this is about 90 degrees Celsius, give or take. Let's take a look at a temperature scalar scene and run this thing. Oh, really? That looks like it's already pretty close to converged. For ease of use, I'm just going to combine those boundaries. I generally don't advise combining them, but we don't need a bazillion different boundaries for this particular one. So let's up this to something like 470 just to make sure it is changing the flow. Drop down our inlet speed a little bit. Right now it's 3 meters a second. We'll go with 1. So what I think we've actually done here is we've overpowered, I think, the convective flow or the forced convection with natural convection. So I'm just going to make gravity 0 for the moment. And this flow should just figure itself out in the sense that it should just flow through directly. Yeah, so without gravity, it's figuring out this sort of flow again. So if we want to measure, let's see here, reports. Let's look at the mass flow rate. How much mass is entering this place? So we look at mass flow. We're going to look at mass flow. Can't see that, sorry. We're going to look at mass flow through the inlet. Oh. Okay, mass flow through the inlet. So it's, according to this, it's, what is that? 0.17 kilograms per second. So let's make this axisymmetric. And we are going to make the axis of our simulation the x-axis, with this being, I need to split this. Can I split this? Split by non-contiguous. There we go. Run up, run down, and I do need to split by non-contiguous, unfortunately. Let's see here. Which one is it? There we go. So this and that are all axis. This is the axis of symmetry. And one thing to note that's kind of important about the axis of symmetry is that it has to exist on y equals 0. That's one additional restriction you get. But let's go ahead and just run a mass flow report really fast once we pause the server. And we can see that, oh, hey, that's a lot less flow. We had, what was it, 0.17 before. Now we have 0.014. That's a lot less flow. And we physically, well, okay, technically we changed it a tiny bit down here. But we didn't change this very much. This is mostly the same geometry, at least two-dimensionally. But because it's axisymmetric instead of three-dimensional, the mass flow rate is much lower. Because instead of proceeding 1 meter into the page, this thing simply exists as effectively a cylinder. If this were three-dimensional, that's only about 1/8 of a meter, a little bit more, in radius. So that's a vast reduction in area. So again, that's kind of a crash course in how to change things from axisymmetric. The big thing is you need to change the continua from two-dimensional to axisymmetric. You need to change the lower boundaries to an axis. The region has some properties, has a physical value for axis, which you want to change to the axis that you're rotating about. And whichever boundaries are the axis must exist on y equals 0. That is, this lower boundary, if we measure this, let me pause this again, we see that these vertices on this lower surface, look at the beginning of this, look at the end of this, doesn't matter. They should be pretty much at y equals 0. I didn't click exactly on them, but if I do this a little bit more precisely, we see that this is exactly 0. Right. 0.1 is exactly 0, and 0.2 might as well be 0. It's like a micrometer or something like that from where I clicked. So again, for axisymmetric, the where'd my domain go? Zoom extents. There we go. By the way, if you get lost in this view, there's a button up here called Reset View, which will bring you back to the default. I do rather recommend it if you find yourself getting somewhat lost. But other than that, that should be pretty much it. Again, it's relatively simple to convert to axisymmetric, but there is a couple of minor important distinctions, and definitely a couple of important steps that you have to do it right. That said, though, I will go ahead and leave it here. That's your crash course in axisymmetric flow, especially if you already have it set up as a two-dimensional model.